we just heard some nice examples of graded summative assignments that were used in the inquiry-based lab examples that we learned about earlier in this module. Sometimes we want to be able to measure students' progress toward our learning objectives, but we don't necessarily want to tie those assessments to the students' grades. In those cases, it can be nice to use tools that have been developed and validated by others for specifically such a purpose. Let's look at some examples of types of tools that might allow us to do this sort of thing. So, one objective that is really common in inquiry-based labs is for students to be able to apply principles of experimental design to answer research questions. Now, you can design your own assessment to determine how well your students can meet this learning objective, and you can use that in either a graded or a non-graded way. However, there's a tool that's been developed by Karen Serum and Jennifer Humberg at Bowling Green State University that's particularly well developed for use in a non-graded system. So this is called the Experimental Design Ability Test, or the EDAT. And it's designed to be used in a pre-test, post-test fashion to determine how much your student's ability to apply principles of experimental design changes over the course of a class. So students are presented with a prompt in which they are asked to evaluate a claim, such as a claim that product X promotes outcome Y. The students provide a written description of the investigative design they would use to evaluate that claim, and it usually takes them about 10 to 12 minutes. The students' responses are evaluated using a 10-point rubric that's shown here. Each one of the lines on the rubric corresponds to a single point, and what you as the instructor do is you determine whether the student has completed that particular element, such as the recognition that an experiment can be done to test the claim, or the identification of which part in the investigation has to be held constant and which part can be varied, and so forth. The authors indicate that scoring is rapid, with 40 tests being able to be evaluated within 1 hour. They also indicate that inter-rater reliability is high and that students' performance on the EDAT is responsive to particular instruction. That is, if you really focus on increasing students' experimental design abilities, that the EDAT is effective in detecting that. Another type of learning goal that is really common in inquiry-based labs is for students to demonstrate an increase in scientific literacy. Now, I have this listed here as a learning goal rather than a learning objective because there are multiple skills that sort of fall within scientific literacy. If you're interested in the impact that your inquiry-based lab has on scientific literacy, then you might want to consider using the Test of Scientific Literacy Skills, or the TOSLS, a test that was developed by Kara Gormley, Peggy Brickman, and Mary Lutz. So this is a 28 multiple choice item test that is designed to be delivered in large courses and to be evaluated very rapidly. It measures 9 different skills that fall within scientific literacy, and these 9 skills fall within 2 categories. So the test determines students' ability to understand methods of inquiry that lead to scientific knowledge. And in that category, we have 4 different skills that the TOSLS evaluates. So students' ability to identify a valid scientific argument, their ability to evaluate the validity of sources, their ability to evaluate the use and misuse of scientific information, and their ability to understand elements of research design and how they impact scientific findings or conclusions. The other category has to do with organization, analysis, and interpretation of quantitative data and scientific information. And the skills within this category that are evaluated in this category have to do with students' ability to create graphical representations of data, their ability to read and interpret graphical representations of data, their ability to solve problems using quantitative skills, their ability to understand and interpret basic statistics, and their ability to justify inferences, predictions, and conclusions based on quantitative data. The test consists of 28 multiple choice items that are contextualized around real-world problems, such as the validity of scientific information on a website, or the validity of a claim about scientific information made within the popular literature. The authors provide a very careful description of the development of the test, and they focus significantly on the validity of the tool, that is, the tool's ability to really measure what it purports to measure. So the TOSLIS can be a tool to rapidly and reliably measure students' scientific literacy skills. And thus, if that's one of your goals in your inquiry-based lab, this might be a tool that you'd value using. Now, you may be interested in affective outcomes in your inquiry-based lab. That is, the impact of your inquiry-based lab on your students' attitudes about learning science or motivation to learn science. One of the best tools that's been developed to measure this type of learning goal is the Colorado Learning Attitudes About Science Survey, or the CLASS survey. This tool was developed by Wendy Adams, Kathy Perkins, Noah Podolewski, Mike Debson, Noah Finkelstein, and Carl Wyman at the University of Colorado Boulder, specifically to measure students' attitudes about learning physics. The survey is designed to be completed in about 10 minutes, and it consists of 42 items in which students' responses are characterized as either expert-like or novice-like within 8 categories, including personal interest, real-world connections, problem-solving sophistication, and problem-solving confidence. The authors carefully described the development of the tool, including how these categories were determined and how the authors evaluated the validity and the reliability of their survey in papers that are available on the University of Colorado Boulder website. Now, although the survey was developed to assess students' attitudes about learning physics, it has been adapted for chemistry, biology, astronomy, and math. And so that expands the disciplines in which this survey might be useful. So, if you're interested in evaluating outcomes in the affective domain, the CLASS survey is a tool that you might consider using. Now, we've tried to present some good examples of assessment instruments that you might use in a way that's not linked to grades. And although we think that these are 3 great examples, they're certainly not the only ones. There are many others. So some other places you might look for assessment instruments that would be good matches for your learning goals and objectives are in your favorite discipline-based education research journal, or at the Field-Tested Learning Assessment Guide, or FLAG Guide, which is found at flagguide.org. This provides a nice compendium of different assessment tools that have been developed. The Science Education Initiative at the University of Colorado Boulder also provides a nice repository of assessment instruments, as does the Carl Wyman Science Education Initiative at the University of British Columbia. So investigating these sources may unearth for you some assessment instruments that could be that you could use to assess your students' movement toward your learning objectives. So we've tried to present you some good examples of graded assessments that can be used to determine how well your students are meeting your learning objectives, or assessments that can be used to determine students' progress toward your learning goals, but not in a graded way. But the take-home message here is not that these are the very best tools or these are the right tools to use, but instead that what's really important is to start by identifying what it is you want your students to learn, and then either design or develop assessments that will really let you determine how well students are moving toward those learning objectives.